Good. So in the equation, the exponent of x variable is positive. And what else besides positive? Alan? Yeah, positive plus whole number or integer. And finally, it's finite difference. Yeah.
The exponent determines the amount of differences there are.
Exponent determines, I'll try and just rephrase that, determines the difference that is the same, right? And there, an example would be x to the 5 fifth differences are the same. Right? Any questions about that? Those are kind of like in summary of our whole lesson there. That's the 3 things we learned. Explain how you can tell whether a polynomial equation is a function and not just a relation. This is kind of a weird question. It's only if so if there's a y or f at x. So if you just see just x squared plus 5, it's a relation. It could be considered a polynomial relation. For it to be a function, you have to have a relationship between y and x. So this is a relation and this is a function. Okay? There, sorry. And the last question here, Kobe, why would these two be examples of a polynomial function?
The exponents are positive numbers.
Yep. We'll answer these two verbally. As the degree of a polynomial function increases, describe what happens to the graph of the function. What happens when we increase the exponent? What happens to the graph? Yeah.
The slope gets steeper.
Slope gets steeper, yep, and it flattens out near the origin. So flattens out near origin, and slope gets steeper. Okay, so we're going to show x squared looks like this. X to the 8 looks like this. Okay, x cubed looks like this. And x to the 11 would look like this. That, of course, passing through the origin. Okay, what happens to the finite differences? The finite differences become the same at the exponent, which we've gone over like 3 or 4 times now. Would you change your definition part C now after having completed part G? I don't remember part C, so don't worry. In summary, a polynomial in one variable is an expression of the form this, where A are real numbers and N is a whole number. The expression contains only one variable with the powers arranged in descending order. So here, all polynomial expressions, you always put the highest exponent at the beginning. 4, 2, 1. In any polynomial expression, the exponents of the variable must be whole numbers. A polynomial function is a function that contains a polynomial expression in one variable. the degree of the function. Remember this, the degree is the highest exponent. If you hear that on the test and what's the degree again? It's the highest exponent in the function, okay? So for example, 6x cubed minus 3x squared plus 4x minus 9, the degree is 3. Why? Because the 3 is the highest exponent, okay? That's a review from 11. The domain of a polynomial function is a set of real numbers, XER. The range of a polynomial function may be all real numbers, or it may have a lower bound or upper bound, but not both. So looking at all of these functions that I've drawn here, these polynomial functions, you're always going to get a domain of XER. Okay? That's another way to tell. All polynomial functions have a domain of XER. Say that one more time. All polynomial functions, domain XER. The range now could vary. For odd functions, polynomial functions, it's YER, but for even, there could be a lower or upper boundary. Okay? Sorry, where am I? The graphs of Polynomial functions do not have horizontal or vertical asymptotes, so they don't have any asymptotes. The graphs of polynomial functions of degree 0 are horizontal lines. That was our y equals 7. So our degree of 0, 0 still being a positive integer, right? So that's addressing that first one.
So can you zoom up a little?
Better?
Yeah.
Yeah, we're just at the end, sorry. So the graphs of polynomial functions of degree 0 are horizontal lines. The shape of other graphs depends on the degree of the function. 5 typical shapes are shown of various degrees. Okay? So although there's kind of these local minimums and local maximum points, it's important to recognize that all of the end behaviors, they call them, okay, are consistent. So even, they both go in one direction. Odd, they go in opposite directions. Even, they both go in one direction. Odd, they both go in opposite directions, okay? And we're going to talk a lot more about that later in this chapter. Okay, that's it. Any other questions with the lesson?